Swayam Prabha. Digital India. Educated India.
Okay, in the last lecture, we looked at passive phase shifters, right? And what we are going to look at now is the uh, same philosophy of trying to get phase shift, but we will get it through active approaches. So, the general philosophy, there are several ways in which you can accomplish it, but the general philosophy is that the input comes in, it goes to a block that generates 0 degrees and 90 degrees, right, relative to each other. So, you have some kind of quadrature generation. And you have some, you can even do it with passive blocks, that's feasible. But basically, you have some kind of variable gain, and then we add it up, right? So, broadly speaking, the idea is that the input comes in and we generate the I part of it, we generate a Q part of it, right? And then to generate any particular desired phase, we scale the I and we can scale the Q. And of course, here we can get amplitude variation also if we want from the same block, right? So, this is the vector interpolator approach. Right? Now, of course, there is a problem here because this is only first quadrant. We need to be able to generate any phase shift that we want. So, we need to be able to generate a vector in all 3 quadrants. So, the way to do that is that you create instead of single-ended signals, you can create differential signal where you can have an I signal that you can access anywhere on this axis. So, you have a VGA that's both able to flip the sign and change the magnitude, and similarly you have a VGA that is able to flip the sign and change the magnitude of the Q signal. So, then you can interpolate to any point that you want, right, by choosing appropriate sign and phase of the I and Q signal. So, if I pick this amplitude weight and if I pick this Q weight, I get here. If on the other hand I flip the polarity of the I and I pick this I weight and I pick this Q weight, right, this also I am able to achieve. So, this kind of block, this attenuator could be in theory passive as well, right? But typically we use an active variable gain amplifier to accomplish this. The key challenge here, of course, is how do we generate this quadrature signal, right? And we have already seen that we can use it, we can use branch line hybrid, we can use coupled line couplers, a LAN coupler is one kind of a coupled line coupler, so we can use a LAN coupler. So, you can get 0, 90 degrees using those kinds of transmission line based couplers at high frequencies, and this is commonly done as well. Now, there is also, I will share a paper in one of the references by Professor Rabai's group, but they have a approach where the quadrature generation is done using a lumped LC circuit, which is similar to the RC circuits that we use as polyphase filters at baseband, right? So we have right. So with this kind of approach, we can create quadrature signals. So you can see here, for example, that as shown in that paper, if we have a voltage here which we call VR, right? And this will be, so at resonance, the current that will flow through both of these is the same because the LNC will resonate, and all you will see from the load perspective here, Vn, you'll see Vn over R, the currents are the same. So what you will see here is VR, and this will be, let's call it VL, which will be this, if I call this I naught, this will be I naught JL omega, and here this will be VR, and this will be I naught times 1 over j omega c, right? So I can basically have a situation where I'm creating if I think of these two voltages, this voltage is VR, right? And then this voltage is VL, right? So VOI will be over here. And this voltage is VR. This is 1 over j omega c. So this is VL, and then VC is over here, right? So then VOQ is over here, right? So now I get a 90-degree phase difference between VOI and VOQ, right? So I can use this circuit to get quadrature frequency. If I call this L and this is C, right? So omega naught is 1 over square root LC. So at that frequency, I can get quadrature using this circuit. But this is, of course, now creating only a single-ended signal. So in that paper, they also generate differential signals by proposing a circuit that looks like so. So with this topology, you basically get a differential quadrature generation. You can show that this is an all-pass filter where around omega naught, the phase difference between these outputs becomes 90 degrees. This is VOI, and then VOI minus, and this is VOQ minus and VOQ plus, where this is your Vin plus and your Vin minus, right? So this approach works quite well to generate a compact quadrature signal, and the uh, overall challenge here is that you're going to get some error when you start loading this circuit, right? So if this is going to an amplifier, right, then when this amplifier is there, that presents, so let's say this is where VOI plus and VOI minus are going, right? So what will happen is that this amplifier will present a loading capacitance here, right? So you'll have some kind of load capacitance because of this. So this quadrature circuit is going to get loaded, and you're going to get an error that is sort of dependent on the ratio of C to CL, right? So if you basically have CL to C, and in their papers they call that alpha, right? So as alpha increases, you're going to get a larger error. So they also propose one way to fix it, right, by adding some series resistances over here, right? So by adding some series resistances over here, you can reduce the impact of the loading capacitor at the cost of higher loss between input and output. So in the ideal scenario, over from here to here, when you analyze this, you see that there is basically a gain of 1 over square root 2 or 3 dB. There's a voltage gain, right? Passive gain as we discussed before. But by applying this resistor in here, we are going to see a few more, a little bit more attenuation. So the loss is going to increase, right? But then the bandwidth is also going to increase. So that trade-off you can make depending upon what your load looks like. So with this sort of circuit, you're able to get bandwidths that are in the range of 20%, 25% with very reasonable error, right? So this is compact as well and can be used to generate quadrature in situations where this kind of passive hybrid coupler or couple line coupler approach becomes too area intensive, right? So once we have generated the quadrature, right, the task becomes to create a variable gain, right? So we need to create the variable gain stage for the interpolation. So what I'm going to do is I'm just going to broadly discuss variable gain, right? Because we also saw that we needed different weights in order to build the phased array. So we need the variable, generally we need a variable gain capability, right? And even variable gain can be done using active techniques and passive techniques, right? We are going to focus on the active technique because that's what we are going to use in the interpolator, right? And after we discuss the active techniques, we can come back to the passive attenuation techniques, variable attenuator techniques. So if I think about active VGAs, right? Approach can be in general we at its simplest, you can think about two broad classes of topologies, one which are current steering and two which are variable biasing or variable GM, right? So broadly these are the categories. So if I want to build a current steering stage, it looks very similar to a Gilbert type mixer, right? So I might have an input stage, either with or without a current source, but I'm just, so let's say for example this gets Vi plus and this gets Vi minus, right? And then I'm this is V control plus, right? And then you can have a ZL over here. Right? Okay. Let's turn it into VDD, let's say, right? And this over here is V control minus plus, and this over here is V control minus, right? So effectively what is happening, so you can either have a current source here or you can have a pseudo differential stage, right? Let's just consider a simple pseudo differential stage, doesn't change things much, right? But basically this stage over here is right? Either VB or a current source below this transistor is setting the current through this these two stages, right? And by changing this V control plus and V control minus relative voltage, I am deciding how much of this current goes over here. If I call this current I1, if I call this current I2, if I call this current I3, if I call this current I4, right? And this is I plus and this is I minus, right? So I plus is going to be I1 plus I2 and I minus is going to be I3 plus I4, right? And on the other hand, if you look over here for I out plus and I out minus, right? So I out plus is going to be equal to I1 plus I3 and I out minus is going to be I2 plus I4, right? So by using the current steering controls over here, I can change the relative values of I1 and I2, and symmetrically what will happen is I3 and I4 will get changed. So then I can basically get this circuit to I can get this circuit to give me variable gain. Just as an example, if you decide to keep V control plus and V control minus equal, right, and the currents split equally, then the output currents are 0 because remember I plus and I minus are out of phase with respect to each other, right? On the other hand, if I decide to keep V control plus very high, all of I1 will go into I out plus, all of I4 will go into I out minus, and I will get maximum gain. And this will also flip the polarity, right? When I steer this current the other way, all of I3 will go to I out plus and all of I2 will go to I out minus. So my polarity will switch. So this circuit provides a way to achieve variable gain, right? And also switches polarity, right? So now this gives me my variable gain on the I side. I can have a similar VGA on the Q side, right? And then I can decide to either have a stage that combines this, or potentially I can, if I treat this as one block, I can have a block which gets at its input Vi plus and Vi minus, right? And another block which gets at its input VQ plus and VQ minus, right? And then in the current domain, I can sum up. So this would be I out plus for the I, and over here this would have been I out minus for the I, and similarly I out plus for the Q and I out minus for the Q, right? And then I have a common Z load connecting both of them, right? So I'm basically summing up the signals in the current domain, right? So this is possible. The one issue here in all this is that there is a lot of interaction between the components, right? In theory, I am keeping the biasing of my bottom transistor the same all the time, right? So if I look in from here, the impedance is not changing, right? And then I am effectively keeping the same load looking up here, because when B control is high, this transistor is on and this B control minus is this transistor is off. Or if you consider the case where this transistor is on and this transistor is off, the load that I see from below looks the same, right? So I'm trying to keep things as identical as possible as I'm changing the gain, right? And when I do that, the hope is that I am able to just get a very linear control from input output. But one of the first challenges is that this V control minus, so if I think about the gain on the I side as a function of V control plus minus V control minus, right, for the I, and the gain of the Q side is again a function of V control Q plus minus V control Q minus, right? If I think about that, what I practically find that there is, firstly, this function f is nonlinear, right? Because this current steering is not a linear transfer function. So then I need to account for that and figure out a way to generate V controls in a linear manner, right? Or to invert the nonlinearity, right? So that's one step. The second thing is that just like any current DAC, when you do this current sum, right, there is, ideally we would want the current flowing through the loads, right? We want the current flowing through the loads to be, let's say I out total plus, to be I out I minus plus I out I plus I out Q plus, right? That's what I would like to happen at this node. But what practically happens is that this impedance is changing when I'm changing this I out plus and I out minus by varying the gain of this stage, right? So when this impedance changes, this current, some part of it flows here, some part of it flows into my output, right? So net result, when I do the current summation, I find that things don't work in a scalable manner, because this impedance looking in, right? So this impedance is, if I call this impedance Z out I, right? So Z out I is a function of the gain that you have applied. Similarly, Z out Q is a function of the gain that you've applied in the Q state, right? So since these two Z's are changing, net effect, what you get is quite a nonlinear relationship between, because ideally you would like to just do a vector sum, right? You want to be able to interpolate between I out I and I out Q to get an I out total that I want, right? But this nonlinear interaction between them creates challenges. So one way to mitigate that is to try to make the ZL, right? Make ZL much less than the Z out of I and Z out of Q, right? If you are able to do that, then you can mitigate some of these changes because of the output impedance. But if we do that, then our total gain drops. So we have a gain issue if that happens. So this is a design trade-off, right? It can lead to, so for example, this is an early result with these kind of approaches, but you can see what I'm talking about, where instead of ideally you would see all these points on an exact constellation plot here, right? Your constellation should look rectangular, right? Because then that means that the I and Q weights are adding independent of each other. Yeah. So what you find then is that all of these currents are adding up. So the I currents don't depend upon the Q and the Q doesn't depend on the I. So you would not have any interaction. But in practice, what we see over here is a constellation that looks like this. You can improve upon this by playing around with ZL, changing the loads, using transformer combining networks, or you could do something that looks like this, where your network looks like so, where you have a quad gen, you have the BGA, right? And I'll draw it as differential because you need differential in order to get the full 360-degree thing. And then over here, you feed this to a Wilkinson, right, to combine the signals. And when you're doing that, you're isolating the I and Q ports with respect to each other, right? So then you can expect a more independent scaling of I and Q. So the scaling of I doesn't depend upon the Q and the scaling of Q doesn't depend upon the I. So this would look a little more scalable. So that is one particular BGA topology, right? Current steering. But there is also, like we said at the beginning, you can make a variable GM topology, right? So in that particular case, there are two possibilities, right? You could have a similar steering topology, right, where you can have your right, and then right. So this is right. So you, in the case of the interpolator, you need one of these for each I and Q. If you're using this as a BGA, you can just use, you just have one input that you're trying to achieve variable gain for. So this effectively works like a variable gain amplifier, right? A differential variable gain amplifier. So the idea here is that this Vin plus Vin minus both inputs go to these transistors. But what we are doing is that we are changing the current through this by controlling VA. We are changing current through this path by controlling VB, right? And that basically changes the GM of these stages, of these transistors, right? And when we change the GM of these transistors, we are effectively changing the current with respect to Vin plus and Vin minus that is flowing over in these four branches, similar to the previous topology, right? And then we are adding them up in order to get variable gain. So in this topology, the control of gain is sort of simplified, right? Because you are controlling the gain by controlling the I, and I is controlling GM, right? So if GM is proportional to I, then you can have linear control. If you see some square root I dependence, you can correct for that by applying appropriate control voltages. So it simplifies control generation. But one of the, so this topology works, but two things to note here are, just like the previous topology that we just discussed, there are two transistors in the stack here, right? So in terms of headroom, right, you need to account for that, right? That's one thing. And broadly speaking, right, when you are building the VGA, you want a phenomena where whatever is your V control, in this case it would have been BA comma BB, right, how you generate that. And let's say this is your gain, right? You want a straight line like this. But if I look at the phase of the signal, right, I want the phase of the signal to be flat across the control voltage, right? I don't want the phase to change, except maybe that if I change the polarity of the controls, then I want the phase to shift to 180 degrees, right? That may be something that I want. But other than that, when I'm achieving variable gain, I don't want the phase to do something like this, right? Because if I'm using it as a VGA, then my problem is that in my system, right? In my system, I have a variable phase cell, and then I have this variable gain cell. But what's happening is that this variable gain cell is impacting the overall phase, right? When I don't want that to happen, I want the phase to be set by this variable phase cell. That's one thing. And if I'm using this in the vector interpolator, then this is going to lead to that same constellation mess up situation where my I is not I, my Q is not Q. So what will happen in this case is that as I increase the magnitude of the I signal, the I, instead of being along the along this point which I am expecting, it will actually look something like this, right? So my I now looks like this. Let's say that my Q also looks like that, right? So what happens with my Q also? So this is the new I, I'll call it I prime, and the new Q across amplitude, the phase looks like this, like this. So if I'm trying to interpolate in order to get some particular phase, right, I'm actually finding that I am interpolating between these vectors, right? So the phase changes, right, as opposed to what I ideally thought. So this sort of error in these topologies primarily comes from the fact that if you analyze this topology, these kind of topologies, you find that it comes because as you are varying the gain, what's happening is that this CGD cap over here, right, is getting modulated by the Miller effect, right, effectively. So you start seeing a variable gain, so a variable phase. So the traditional approach is always to cross couple, and once you are or to neutralize, sorry. So once you are ready to do that, you can even get away with a single stage design where your amplifier looks effectively like this. Right. Repeat, right? So this is what the lower part of your amplifier looks like, and then in order to solve the CGD problem, what we do is we can do the neutralization this way. Right? And with this kind of sorry, this should not have been VA. This is also VB, right? But VA because you're just changing the differential gain. Yeah. So what we then do is we are varying the GM of this transistor, right? The GM of this transistor is changing when we change VA, right? And you can show that if you don't do this, right, then your gain is has this GM minus J omega CGD, right? So as you change, so the angle basically becomes tan inverse omega CGD over GM, right? So if you are changing GM to change the gain, you are changing the angle also, right? So with this neutralization approach, right, your gain becomes proportional to just GM, right? So as a result, this CGD dependence goes away. So your phase dependence, your phase variation with gain control gets reduced, right? You can also, if you worry about the fact that this doesn't track process and things like that, do the sort of current steering approach, but creating a Vn plus stage, right? And we are so you can basically compensate for, so this is the B in minus stage, right? But you would like to ideally have another stage to compensate for this. So you create a B in plus stage and a B in minus stage again, right? And now these two topologies have this thing. So then in order to balance the currents, you can just take this node over here, right, and connect that to this one, and you can take this node over here, right, and connect that to this one. So this basically again creates the same sort of neutralization structure, right? The challenge with this is that again you're operating on one level, right? So any resonance that you have in this can impact your input matching. But again, because you are sort of neutralizing, you can create a better immunity to the changes here. Implementations here, right? So you can see the variable gain stages, right? And we can look at the relative phase shift across gain settings. And what we see over here is we get something like a 6 to 7 degree error across phase, right? So these are all sort of the neutralization approaches, right? But there is also another approach with the current steering itself, right? Where what we do is we have this input stage that is creating the current, right? And then we can create these these transistors here, where when this transistor is enabled, the current flows through here, and when this transistor is disabled, right, the current and this transistor is enabled, the replica transistor is enabled, the current flows through here. So the current that is that is coming through this particular common source stage can either flow through to the output or it can flow into VDD, right? The challenge here is that in order to again reduce the gain versus phase dependence, we need to make sure that the impedance that we see over here looks constant, right? Otherwise, there is an issue, which is why this replica stage helps, because if I think about looking down into that stage, right, either this transistor is on and this transistor is off, or this transistor is on and this transistor is off. So if I look from below, my impedance seems fairly constant, right? So this goes to VDD and this is connected to the RF out node, right? So my impedance stays constant, but there is still a dependence that happens because of the CGS capacitances, right? And then in order to fix that, they propose adding this series inductance between the common source and common gate load, and you can sweep the value of this LD by looking at this phase variation across gain settings, and then you find that there is an LD which takes out the impact of this particular CGS and CGD variations, and you can get fairly uniform gain, fairly uniform phase across relative gain. So in all of these topologies, one thing we can also notice is that while we can keep the delta phi to low single digits across gain settings, the gain variation itself is only of the order of 7 to 10 dB. If we want to get really high gain variation, then this phase, delta phase is also going to increase. So then at that point, what we have to do is cascade multiple such VGAs in order to get a larger gain variation while also keeping delta phi constant, right? So from a topology perspective, you can design a neutralized common source or current steering to both work this way in CMOS. In the case of your CDHBT, we have one slight change there, because so in this paper they talk about this option of looking at the model of the BJT this way, right? And if you don't have the resistance RE, then GM effective looks like GM divided by 1 plus J omega RB CJE plus C pi, right? So as a result, what we are basically going to see is that we are going to see an angle that is omega RB CJE plus C pi, right? And what happens is that when I vary GM, my C pi is going to change, right? And as a result, the angle is going to change. So if I'm, so what they propose is adding this RE, right? And then if you look at the transfer function, you can basically show that the phase variation looks something like this, where it is RB plus RE times 1 plus C pi over CJE divided by 1 plus GMRE times omega CJE, right? So now remember that when I change GM, my C pi is changing, and that is the source of the issue. So if I am able to ensure that, for example, something like this, right, then I can cancel out these two terms and I would get something that depends only upon parameters that are not changing with my GM, right? So there is an RE that is optimal in this particular case, right? And what they are able to show is that, for example, if they use an RE of 20 ohms, right? So as the if you consider an amplifier where you are changing the current to change the GM, you can still get a very flat response in phase across bias current and therefore GM, right? In a bipolar, the GM is going to be IC over VT, right? So by changing IC, you're changing GM while keeping the phase constant, right? So they use that technique in this amplifier where they add this source degeneration RE resistances, and then we can see here that the measured performance shows that the phase error is or the phase variation is pretty small as the bias control current is changed, right? So from a VGA perspective, then of course, just like the phase shifter, we have in addition to the variable gain, other specifications such as linearity, noise, and things like that, right? So using one stat with neutralization or only one transistor with neutralization that we just saw can help with linearity, right? And still maintain low phase error across variable gain. And if we are looking at the reason for the change, variable phase with variable gain mechanism in bipolar, we can add this sort of feedback or source degeneration in order to improve this dependence. So there are so to complete the thread on this, we started the VGA discussion with saying that we have this vector interpolator approach to generate phase shift. So we can get this, we need a variable gain, right? But broadly speaking, in any phased array, when we need the variable gain cell, we can design it with similar approaches as we do for the interpolator. Sometimes in several architectures, what we often find is that 0, 180 is a differential phase shift. So it's easy to accomplish using active stages, right? So you'd have hybrid phase shifting schemes where we could have a passive phase shifter that provides 180 degrees of fine resolution, right? We saw the loaded T-line phase shifter that does that, or the reflection type phase shifter, or some bits of switch type phase shifter. And then we have a variable gain amplifier that is providing the variable gain and also implementing a 0 plus 180 degree coarse phase shift, right? So this basically gets us both the variable gain and variable phase efficiently. So we don't have to add another block to get the variable gain. The vector interpolator, obviously, it can create any particular point inside the constellation, right? So if this is your I mats and this is your Q mats, right? It can create any point inside this, so it can give you variable gain and variable phase as well together, right? But in all these cases, generating the control voltages and generating calibration values are challenging and are usually done based on simulation because things will slightly change from theory in all of these cases. But we also saw that the gain variation can be somewhat limited, and the other challenge in all this is linearity. So if you are using an active variable gain blot, we have to worry about the linearity of the blot when we design. So there is a place for passive attenuators as well, and we like to make them variable in order to achieve linear variable gain across the cell, right? And we like them to be compact as well. So again, here many different approaches are possible, and it's important to note that while the passive might solve the linearity issue, it also has gain and phase dependence, right? So that still is something that we have to design for. But we can do similar approaches just like for the switch type phase shifter, right? Where you have two different paths, and this path has a fixed attenuator, right? And this path maybe has no attenuator, right? So we can switch between these two in order to get variable gain. The fixed attenuator itself, if we want to look at it, there are, just like for the phase shifter, there are resistive networks that, so you get T-type resistive networks, right? So for example, if we consider a network that looks like this, R1, R2, R3, right? And we define basically K as the attenuation factor, which is, let's say you want a certain attenuation, right? Right? So just as an example, so for 3 dB attenuator, right, K will be equal to 1.414, right? And for a 6 dB attenuator, K will be 2, right? And with this, you can basically design, the design equations look something like this, right? Right? R1, R2, and R3 is there in the network. So R1 is typically equal to R2 in this branch network, and this is R3, right? So you can implement a network like this, right, which is a pretty popular approach to get a fixed attenuator of while being matched in impedance to 50 ohms. And on-chip resistors have low capacitor parasitates. So this kind of network works well, right? And there is a pi equivalent for this. You can do unequal impedance matching. These are all in literature. You'll be able to find it, right? The one other type of network which is useful to know that it exists, right, is a bridged T attenuator. And because in this particular case, in order to vary the attenuation factor, you have to make 3 resistors variable, right? So that becomes an issue. You can build a network that looks like this. Right? And then you have R3. And here typically, so R1 is just your Z0, R2 is R1 divided by K minus 1, and R3 is R1 times K minus 1, right? So in this case, you are varying this resistance and this resistance, right? For a particular Z0, if you vary this R2 and R3, you can control the attenuation factor through this. You can implement some modules of this, right? So this basically looks like some parallel resistances with some switches, right? And similarly, this over here is implemented as a network of parallel resistances with some switches, right? And we can achieve attenuation. Now, of course, the problem is that this switch has a model of R on and has a model of C off, right? So when it is off, it's going to create some capacitive parasitates that exist in the system. So you can't have a very large array of switches or try to get very small R on. There is a frequency limitation, right? And there is also the fact that each of these switches is going to have some insertion loss. So if I'm trying to make this instead of fixed, I can make it a variable attenuator by doing the tricks of putting switch resistors like I showed, right? So you can make this a variable attenuator, but still, we have to incur the insertion loss of this switch as well, right? So that sets a minimum on the performance that we get, right? And typically, again, if you try to make multiple stages of this, you have to pay that penalty as well, right? You can find out in the technology of in your technology what the sort of order of magnitude switch losses are by taking a single switch and simulating that, and that basically helps you make the decision on appropriate choice of topologies, right? So when I'm running an interpolator, let's say that ideally I am living with a Q signal with this as my Q max and this as my I max. Yeah, so that's what you have, right? But then what happens is that when you implement it in layout, you find that your Q is no longer like this. Your Q basically is starts looking like this, right? So there are two errors that you can have. One is that your amplitude of your Q is more than I, right? And the phase that is there is no longer 90 degrees, right? So this is similar to IQ offset in the circuit, when we design receivers, for example. So this does happen, right? And what the challenge becomes is that typically this also means this, right? Right? And so now what I will effectively find is that I thought I'm interpolating this weight and getting to here, right? But now I'm interpolating something that is over here, right? And getting to this point, right? And so I have an error in the vector that I targeted and the vector that I got, right? So this basically is some sort of error that I am getting in my phase, right? And if you don't fix it in layout, if you don't compensate for it in layout, you effectively have to compensate for it in weight generation, right? It is better to compensate for it in layout because that compensation has to happen somewhere, right? You are better off trying to make sure that your layout is as close to quadrature as possible so that when variations happen, they happen around the nominal, because mathematically you can get away with this. There is just whatever you do in the layout in order to compensate to bring it back, right? For example, let's say that a classic example is a quadrature coupler let's say that this is 0 degrees and 87 degrees, right? Instead of 0 degrees and 90 degrees. The question is, do I just accept the 0 and 87 and interpolate between that, which will work? Or do I add an extra 3 degrees of transmission line here so that this point becomes 0 and 90, right? The traditional approach is to do this, is to get to the point where in layout you're generated as quadrature a design as possible so that your weight generation is easier, right? That's the traditional approach. But typically you can compensate for those kinds of small errors by routing or creating meanders in the design to compensate for it, right? The only this is like a deep implementation issue, but what really causes problems is if the input of the amplifier, right, its Z is changing with gain, and then we have added some compensation networks over here, right, and then the Z over here is changing with gain. So then whatever is generating the quadrature, right, the quadrature error itself starts changing with the gain, right? So then you really have an issue, because if this Z in is a function of the gain, right, then the angle that this is generating itself starts depending on the gain. And at that point, there's just no straightforward correction for that. So it's better to divide the design into objectives such that you make sure that this Zn, this is not true, that this Zn stays constant to some Z0, right? So you have to break the design into steps. Otherwise, the interactions just make it very difficult to design. Mathematically, it all works, right? You can put all of this down, measure it, and then find a set of weights that will generate the constellation points that you want. But then you'll find that those weights start changing across frequency and changing across, and they vary in a nonlinear manner. So that means in practice, the control voltages that you have to generate, right? So for example, you might find that I generate this control voltage with 5-bit precision, but I get only 4-bit of phase shifter precision, right? That's basically what typically happens. But we do that. We do generate the control voltages with higher precision than the phase shifter, because it isn't too expensive to do the control voltage generation of higher bits. I mean, that's not too much of a problem in CMOS. You have to design for it. You have to, yeah, you cross, when you do the CGD neutralization, for example, you have to design for it. There is none of these blots are inherently PBT resistant except some techniques like that RE opt for GM, right? That is somewhat PBT resistant. So you have to find either circuit tricks like that, but there is really no magic there. You can include tunability in your quadrature generation. So for example, this C can be a variable C, right? And try to account for some loading changes by compensating for that with this C, or if the C is changing across process, to recenter it back to where you need it, right? Those kind of tricks people play, but that's not you are moving the problem to a later day, because then you have to find out how you are going to calibrate it in measurement at volume, because that's not easy either. So the techniques that you're trying to do, like neutralization, etc., are what sort of make it process invariant. Yeah. So coming back to passive attenuators. So we saw resistive attenuators. The other popular passive attenuation approach is to just take a transmission line, right? And we saw that the attenuation constant was dependent upon the series resistance and the shunt resistance, right? So what we do is we add some shunt resistance to it periodically. Right? And by using this kind of approach, we can achieve variable phase. The challenge here is, of course, that this is effectively changing the impedance of the line looking here, right? So you're going to see the same situation where if I look at attenuation, and I look at phase, right, I'm going to start seeing a non-uniform phase again instead of a constant phase, right? Particularly if I try to make this R very small, right, to get a lot of loss from just one shunt resistor, right? So the way to do this is to have many sections, and you can show that you can get small phase shift if you make all of these sections lambda over 4 long, right? And then put these shunt attenuators over there. But clearly creating a lambda over 4 section for each particular resistance starts getting big. So there are some, again, implementation examples here where you create, we basically do a few things, right? So the structure looks something like this. So you have transmission line, and then these load shunt resistors that are being placed periodically after each section. Now, in order to compensate for the phase error that is being caused by these shunt resistors, add another T line over here below the shunt resistors, right? So that's one step. And then you can lambda over 4 will provide the best most constant input match and low phase variations. But what they do is they sweep the length of each section, right? And they decide, okay, this is the S11 looking in. So even if I use 22.5 degrees, I get an acceptable S11, right? I don't have to go all the way to 90 degrees to get the least variation. So then we decide that, okay, we can keep an acceptable 22.5 degree S11, and then in order to the one thing to note here is that each of these sections is 4Z0, right? But they have 1 dB attenuation steps, right, in this. But in order to achieve these 1 dB attenuation steps, there is a pattern of activation here, right? It isn't that you first activate this, then you activate this, and then you activate this. It isn't like that, right? In order to get multiple dB attenuation in this paper, they show the pattern that they are using. So they have 12 of these steps, right? And then by controlling different number of so technically you have 2 to the power 12 possible states, right? So you have thousands of states that are possible. But in those states, you try to find a subset of states where you're trying to get 1 dB attenuation step with wideband performance while being able to get away with a short transmission line, right? So, once they do that, if you notice in this figure, what they are plotting is the relative insertion phase variation as a function of electrical length. But without this TL2 sections, if you really wanted to minimize the phase variation, you would have to use TL1 length of 90 degrees, right? But we already saw that short TL1 can be okay for input match. But if we make phase variation the metric and we add TL2, a short TL1 also can be acceptable for low phase variation. So of course these TL2 sections also add some electrical length. So this is a 30 degree section here. So instead of one 90-degree section, you have a 22-degree section and a 30-degree section, right? So that's basically the trade-off. But with this sort of approach, what you can get, attenuators are typically quite wideband, right? Those resistive attenuators that we just discussed, those bridge type attenuators or T-type attenuators are also quite wideband. So with these kind of passive attenuators, you can get wideband performance with reasonably good gain versus phase variation. You can see that the size of this attenuator is about 200 microns by 750 microns, which can be a little large if you're trying to build a very dense, compact, large phased array, right? So one approach to mitigate that is that we basically, instead of just putting a one Z0 switch in a section, right? We put multiple Z0, multiple 4Z0 switches in the section, right? And then try to again, maybe the penalty also becomes that you have to increase the transmission line length a little bit to still make sure that you have acceptable matching and phase variation. But because you have each cell, instead of nominally giving you 1 dB, by activating VC3 or VC1, VC2, right? So let's say you have it as a thermometer system where 0 is when you activate 1, you get 1 dB, when you activate 2, you get 2 dB, and when you activate all 3, you get 3 dB, right? You are basically reducing the total number of sections that you need in order to get a large attenuation. And the other thing that they do over here is that instead of implementing that MOS, resistance switch as just one resistor, they implement it as a stacked series of transistors. So the benefit here is that I can tolerate a much higher voltage swing on this line. So then be much more linear without this switch, because otherwise the switch resistance starts getting modulated, right? So we can do some things like float that switch control voltage, right? So then as this swing goes up and down, this gate swing also moves up and down along with it, right? So, and what we then do is bias this gate up, right? So then this is not moving about 0, this is moving about VB, right? The gate is moving about VB. So then if you make sure that the lowest and value of the highest value of VB is not going to break anything down, and you are able to, for example, push VB below 0, then you can make sure that the transistor doesn't turn on during the cycle, which enables higher power handling in the device. The other approach is to stack multiple devices so that things stay linear for a larger swing. But again, you can see the performance here. You're able to handle power levels of more than 15 dBm in the device. But the size they implemented also, in addition to this, sections where instead of these being terminated in the ground, they were terminated in a similar TL2 type structure, right, to compensate for the phase. So they have a couple of implementations. So the phase variation again in these cases can be in single digit degrees of phase shift across the overall 10 dB plus of gain variation, right? So if you want to build a wideband attenuator, building a passive resistive attenuator or a transmission line that is loaded, that kind of attenuator works very well. And particularly it's very useful because many times inside the cell you have a lot of routing from one point to the other. So you can reuse the routing to implement a variable attenuator by adding shunt attenuators or the resistive networks inside it, right? So that's one option. The VGA type approaches work very well for narrow band schemes, where you do want certain gain because you don't want to take. So for example, in this case, the minimum insertion loss is 4 dB, right? So you don't want to take this insertion loss. Instead, you want to amplify the signal and have variable gain. So that approach works pretty well. Last component that we need in the array, now that we have the variable phase and the variable gain, the last array specific component that we need is an ability to combine signals from multiple elements, right? Because in all of the array uh, uh, topologies that we are talking about, we are summing these signals up, right? So we need a way to accomplish this summation, right? And you can again do this summation several different ways. It can simply be a current summation where you have over here you have a GM stage, right? And another GM stage. And all we are doing is just dotting the currents together into a load, right? This is possible. So this is an active summation approach, right? Or many times what is really useful for us is to make sure that there is isolation between these two elements so that the phase change or the variable gain setting of one element doesn't influence the gain and phase of the other element. So to get that isolation, we turn back to our Wilkinson combiner, for example, which gives us this isolation between these two ports and then combines the signal between them, right? So this can be a pretty wideband combiner. We already looked at the lump versus T-line implementation, right? So you can make pretty wideband combiners even if you use lumped implementations of the Wilkinson. So this is just an equivalent pi section network of this. The one issue here can be that when I'm summing signals from different elements, right? They are on the chip, they can be located quite far away, right? So I typically do have this situation where I have to route and this is usually these lines are long enough that you have to do them with impedance defined transmission lines. But basically you have these long lines that then go to the Wilkinson, right? Because the Wilkinson does need these resistors over here, the 2Z0 resistor to provide isolation, right? And that 2Z0 resistor, you would like it to be right between the inputs. So the Wilkinson does like its inputs to come close together, right? There are other passive combiners that address this issue by allowing you to build combiners where this is a Geisel combiner where it also provides isolation between these two ports. But you can see now that there is a pretty long transmission line in between port 2 and port 3, right? And this means that you can take your routing network itself to be part of your combining network and then isolate. Now, one disadvantage of the Geisel can be that this is actually a full wavelength, so it might be too big, right? And you can play tricks here where the Geisel, if it is a differential Geisel, you can take 180 degrees of phase shift by just swapping the wires after 90 degrees. So this is 90 degree, this accomplishes 180 degree, and this accomplishes the next 90 degree, right? So you can incorporate routing into the combiners. But again, the key metric here of building these kind of passive combiners is this, which is that you want isolation between these two ports so that the impact of one port doesn't affect the other. Now, just a little emphasis here, which is that if I consider a Wilkinson, so in the Wilkinson power combiner, right? If you have P in and and this is port 1, right? It's important to remember that the transfer function from each of the inputs to the output, the magnitude of the transfer function is 1 over root 2, right? So what does that mean? That means that if we think in voltage terms, if I apply V in over here, right, this is going to be, or let me call this V3, this is going to be V3 over square root 2, right? And if I apply V2 here, this is going to add up then V2 over square root 2, right? And if V3 is equal to V2, because I've shifted the phase and made sure everything is the same, then I get basically, let's say that this is V element, right, the voltage that's coming out of the element, then I get basically VL times square root 2, or power in each element plus 3 dB, right? So the power is getting combined. But if I don't have one of the inputs, right, if I only apply this input over here, right, the P1 will be P into minus 3 dB, right, because only this 1 over root 2 will be there. Half the power will be dissipated in this 2Z0, right? So the Wilkinson is not a lossless combiner, right? It appears lossless when you apply in-phase inputs on both sides, right? If you don't apply in-phase inputs on both sides, then it is not going to be lossless. There is going to be loss in the combiner, right? That's something to note. So what you cannot assume is that I don't apply this input, and the Wilkinson normally, when we apply the same phase inputs, it appears lossless. Then you can't assume that this P in 2 will lead to a P in 2 here. There is 3 dB of loss that happens. One thing to worry about in all these combining and distribution networks is the impact that it has on linearity and noise, right? In linearity terms, if I'm designing a transmitter and I have this kind of configuration where amplifier A is driving amplifier B, right? I see that my amplifier B has an OP1 dB of 10 dBm. I lose some output 1 dB power in this particular case. Now let's say I have the same situation with 2 elements. Then because I'm driving this power and splitting it to both sides, I effectively lose 3 dB of power in the Wilkinson. So my effective output 1 dB of my signal chain drops, right? And this is also exacerbated if I have loss in my Wilkinson, because then my power will be more than 3 dB less. It will be like maybe typically around 4 dB less, right? And if we start modeling that and we start building, for example, a 4-element array with a single driver amplifier driving all the signal chain, we can see that the OP1 dB effective is continually dropping. And clearly by the time we get to 16 elements, we are completely wasting the OP1 dB of this amplifier. We are completely limited by the OP1 dB of this amplifier, right? So it's important to design your array TH signal distribution, keeping in mind whether what is driving is providing enough signal power that after all your signal splits, your last chain amplifiers are still able to work in a linear, are still able to achieve their OP1 dB, and you're not limited by the OP1 dB of your driver amplifier. You could put an amplifier there, but the trade-off basically becomes that if I put another amplifier here, in a 16-element array, I'm increasing my power by 16x because I have to, and my area by 16x, right? If I could insert that amplifier here and it would have higher OP1 dB, then potentially I'm not increasing my area that much, right? So it becomes a question of where in the signal chain can you place that amplifier that gives you the best balance of power and area, right? So that's why typically you have some stages of active distribution in the middle, right? So what does an active distribution stage looks like? Typically equal current split, but it's in P in N and then just an equal current split, right? So this is, if this is ID, this is ID over 2, this is ID over 2, right? So all we are doing is just splitting the currents by a factor of 2, and thereby just getting power split between these stages, right? And what works as a power splitter, also the approach works as a power combiner, where in this case I have two inputs coming from elements, and just like I drew, right, we are basically trying to build a high GM stage, right? And we are just summing up the currents that are coming out of those GM stages, right, into a common load. And clearly this whole combining would work a lot better if the Z out, right, of the GM stage is high, right? So that's why we in this case use a cascode to increase the impedance looking down over here, so that you can create the current sum. Now this kind of technique, for example, even in the vector modulator where you are combining, you can add a cascode, but the problem there becomes that then you're potentially looking at 3 levels of transistors that might compress. But again, all those traditional techniques of trying to improve output impedance hold at millimeter wave as well. And these kind of active combining and distribution stages, right, we consistently insert in our network, right? So this is from this paper where the RF mixer output comes in. There is one driver amplifier here that splits it into 2. So there's an active 1 splitter, and then there's passive splitting, and then there is again an active splitter that appears, and another stage of passive splitting that finally leads to the output, right? So this is a way to balance the gain and linearity requirements and the number of amplifiers that we are inserting in the chain. Now this is dependent on frequency, technology, all of those parameters matter here, but it's something to be aware of in the system design. So typically the right approach is to do a system spreadsheet and then insert the amplifier and look at cascaded linearity as an impact. On the signal combining side, whether we do an active combining or passive combining actually depends on more on system usage metrics, right? Because if we consider a situation where all elements are active, right, then effectively by the time there is some insertion loss that is associated with each Wilkinson, right? But the array signals are combining together, and since they are combining in voltage, because we have made sure that they are in phase, effectively what's happening is that the signal is sort of getting combined and getting stronger and stronger as it goes through your passive combiner chain. So from a noise figure perspective, it's less impacted by these insertion losses, because as more and more elements add, the signal amplitude is increasing as n, right? But one thing that can happen in the array is that people might operate it by deciding that they want to have a reconfigurable number of elements where only 4 elements are active or only 8 elements are active, but the distribution state stays the same. So for example, just to consider a 2-element array, if I decide not to have this signal here, then this Wilkinson is a -3 dB loss. So effectively, I'm following up my gain with 1 dB, -3 dB, 1 dB. So by this point, I have lost 5 dB of gain. So I can think of this driving with a 13 dB gain, basically, effectively at this point, right? So this then makes the impact of the noise figure of follow-on stages important, right? So you can again, the right approach is to look at possible usage scenarios, figure out the models for all these distribution networks, and then consider what happens to the SNR, right? So in this particular case, for example, we look at the number of active elements, right? So this is a 16 element array, and the potential is that it would operate it as just a 1 element array or all 16 elements active. And this is if you assume that only passive combiners are used, and this is with an active combiner, right? And what we are looking for is we expect that the array noise figure improves by 10 log n as we increase the number of elements. But because of these insertion losses, we are not going to get 10 log n, right? So how much do we lose? That's what this is a metric of, right? And what you see is by inserting an active stage, then with by the time you reach 6 or 7 elements active, you can saturate out this how close you get to 10 log n, right? If you want this to work even with fewer number of elements, then you have to have not just one active combiner, but maybe even more active combiners, right? Because the active combiners don't have loss, they have gain. So they protect follow-on noise figure pretty effectively. So the circuits for implementing the combiners, again, are either hybrid couplers or just current mode combiners, right? The circuits are pretty standard. But the interesting thing here is to make sure that you're architecting your number of combiners that you have in your signal chain carefully to balance noise figure and linearity.